Okay, so now we're going to start with chapter 14, which deals with liquids and solids. So, firstly, we're going to start talking about a liquid and what do we mean by this term. So, the liquid state, as you know, has properties intermediate between the gaseous and um, the solid state. Now, when it comes to gases and liquids, there are some comparisons between the two. There are some things, properties that are common to both of them. For example, they take on the same shape as the container that they're in. But one big difference between gases and liquids is that unlike gases, liquids have a fixed volume. Gases, of course, its volume is not fixed because it expands to take up the whole space of the container that they're in. So let's look at some other properties of liquids. In terms of what happens at the microscopic level, the particles are close together. The liquid is incompressible. That's a big difference between a liquid and a gas. Definite volume, as I said before, and it takes the shape of its container. That's one thing it has in common with a gas. And those are the properties of liquids. Now, let's talk about the process of evaporation. We all know what that is. Evaporation basically takes place when you have molecules escaping from the liquid state of a substance to the gas or vapor state. So this is basically an abbreviation of what happens in evaporation. And what you'll find is that as the molecules escape into the vapor state, what you'll find is that those molecules tend to have a higher average kinetic energy, which means that the molecules remaining will have a lower average kinetic energy, and therefore the molecule or the molecules that remain behind results in the liquid remaining behind being cooler. And therefore that's why liquids, when they evaporate, they exert a cooling effect on the substance that or the material or even the skin, for example, that it may be on. So this is what happens when water evaporates. It goes from the liquid state into the gaseous state. So that's evaporation. Now sublimation is a different process in that we have the direct conversion of a solid directly to the gaseous state without going through the liquid state. All right, and one example of that is the sublimation of iodine. If you heat a sample of solid iodine, then that solid will go directly into a gas. So that's an example of sublimation. Another one that you might be familiar with is frozen ice, or frozen, I should say, carbon dioxide, which is also known as dry ice. As you all should know, if you have played with it, dry ice, if you leave it on a surface at room temperature, it goes smaller and smaller without any liquid residue left behind, and that's because the solid carbon dioxide in dry ice is converted directly to gaseous carbon dioxide. So those are two examples of sublimation. Okay, let's talk about the concept of vapor pressure. Vapor pressure is the pressure exerted by a vapor in equilibrium with its liquid. So in other words, we're talking about this, where we have the liquid being converted to the vapor, and at the same time and the same rate, the vapor is itself converted back to the liquid. So the forward process in this situation is evaporation, of course, and the reverse process is condensation. So when you have those two processes occurring at the same time and at the same rate, then basically the pressure exerted by the vapor was called the vapor pressure. And in a closed system, what happens is that after a liquid evaporates, some of the vapor molecules will strike the surface of the container and return to the liquid by condensation. So that's how basically we have that back and forth taking place between those two states. Now, if you have a molecule, or I should say a beaker with a liquid in it, and you leave it open over an extended period of time, then what happens is that all the molecules will escape the liquid state and end up in the vapor state and escape into the atmosphere. So that's what happens in an open system as we see here. Now, if the system is closed, as we see in this diagram here, then you won't have all the liquid drying out basically, because what happens is that as soon as the vapor is formed here, if enough of it is formed, then they have nowhere to escape, so some of it will go back into the liquid state, but at the same time you'll have some of the liquid going into the gaseous state or the vapor state. So you'll have that back and forth taking place between the two. And eventually you have a state of dynamic equilibrium between both the liquid and the vapor state. Okay, so now we're going to look at how do we actually measure the vapor pressure of a liquid at different temperatures, namely 20 degrees Celsius and 30 degrees Celsius. Now, the liquid that we're working with is water. And a couple of things I want to say before we get into the actual process. The vapor pressure is independent of the amount of liquid and the vapor present. And it's also important for you to note that it increases in temperature. And in fact, we're going to see that in this exercise. So here's the setup for determining the vapor pressure of water at different temperatures. So here you'll notice that the temperature is set at 20 degrees. All right. So let me just describe this apparatus. So we have our flask, which is connected to a manometer right here. And the manometer is basically an instrument that is used to measure the pressure of a gas or a vapor. And you'll notice that in the manometer, which is a U-shaped tube, you have mercury. And in this flask, you have nothing, because here it's connected to a vacuum. So the vacuum sucks out all the air from the flask. So there's nothing here in the flask. In other words, it's a vacuum. All right. And as a result of the fact that you have a vacuum here and a vacuum here in this end of the manometer, that means that there's no pressure exerted on the surface of the mercury here or here, and therefore the mercury levels are the same in both arms of this instrument. Another thing I want to point out here is that you have a flask, or I should call this a separator funnel, which contains water, and of course the stem of the funnel is leading into the flask. All right, so this is the basic setup for this experiment. Okay, so we start adding water into the flask. All right, and eventually what happens is that the water begins to evaporate. And then what happens is that because the water evaporates, the vapor will start exerting a pressure here on this end of the manometer, which pushes the mercury level up here in this end. All right. So therefore, pressure exerted here, there's no pressure here in this end. So therefore, the mercury levels here, the height of the mercury levels, or the difference between the two mercury levels, will be proportional to the pressure exerted by the vapor. Now, when we get to a stage of equilibrium where the rate of vaporization is the same as the rate of condensation, then we can measure the vapor pressure of the liquid, and that would be represented by the difference, as I said here, between the two mercury levels. And in this case, at 20 degrees, it turns out to be equal to 17.5 atmospheres, or torr, I should say. Okay, so that's the vapor pressure of water at 20 degrees. Now, what if we increase the temperature to 30 degrees? Well, what that means is that the equilibrium will be pushed so as to produce more vapor above the liquid surface, above the water surface. So when the equilibrium is reestablished, there's a greater amount of pressure exerted here, which will be exerted here, and therefore this pushes the mercury level down even further and increases the distance between the two mercury levels here, and it turns out to be 31.8, and that would be the vapor pressure of water at 30 degrees. All right, and we can continue to increase the temperature and monitor the vapor pressure as the temperature increases. And in fact, there are tables that are published which gives you the vapor pressures of water at different temperature. So this is one such table which shows you the vapor pressure of not only water but two other substances for comparison, namely ethyl alcohol and ethyl ether. But for now, I'm just going to focus on the water. We're going to talk about the comparison when it comes to the other two substances later on. But as you can see, as the temperature increases, the vapor pressure of the water increases. All right, and that is true also for the other liquids, right? True for any liquid. For any liquid, as you increase the temperature, the vapor pressure of that liquid increases. All right. Okay, so the vapor pressure at any temperature, if you compare these three liquids, is ethyl ether has a greater vapor pressure than ethyl alcohol, and the vapor pressure of ethyl alcohol in turn will be greater than the vapor pressure of water. So that is true at any temperature. If you compare the vapor pressures of the three substances, you'll find that ethyl ether will have the greatest vapor pressure and water will have the lowest of these three. As a result of that, the rate of evaporation will be the same, right? In other words, ethyl ether will evaporate at a faster rate compared to ethyl alcohol, which in turn will evaporate faster than water. Okay, so that's basically the comparison of vapor pressures of these three different liquids. Okay, one more thing I want to mention, volatility, before I end this video. Volatility is basically describing, when we use the term volatile, we're saying that the substance vaporizes relatively easily. So the more volatile a liquid is, the easier it vaporizes, basically. So again, going back to those substances that we were talking about, ethyl ether would be the most volatile of the three liquids, right? So as you can see here, the vapor pressure of ethyl ether, which at room temperature is 442.2 torr, that is considered for most intents and purposes to be volatile. Water is considered to be moderately volatile. As you can see, its vapor pressure is, 17.5 torr. And then mercury, as you can see, its vapor pressure compared to the other two is very low, right? 0.0012 torr. And therefore, for all intents and purposes, we consider mercury to be a non-volatile liquid. Okay, so that's basically it for the introduction to this chapter. So the next video, I'll be talking about surface tension. Until next time.